All right, so let's see. We're going to move on. So, what are we going to cover today? Topics for today: concentrations and loading calculations. We've got concentration. We'll do a lot with the pounds formula, biological oxygen demand (BOD), and we'll talk about organic loading. So, the first thing as part of this, we want to talk about is concentration, and concentration can be looked at a few different ways. We look at it as milligrams per liter or parts per million. Those are the same thing. It can be confusing, but they are the same because we're looking at, when we talk about parts per million, we're talking about the parts per a million, the number of milligrams per a million milligrams, and 1 liter of water weighs 1 million milligrams. So those two are equal. We could talk about things in percentages. A percent is 1 part per 100. It can be expressed as a fraction. It can be expressed as a decimal. But when we talk about percentages, it's typically taking that decimal and multiplying it by 100 to get what the percentage is. For our if we're looking at things in parts per million, 1% is equal to 10,000 parts per million. So that's basically saying that there's 10,000 parts out of the 1 million parts. Okay, so that's equal to 1%. So but it would be 10,000 parts per million is equal to 1%. And then part per million is equal to 1 part of solids per 1 million parts of water. So let's look at some examples of concentration. What is a concentration in milligrams per liter or parts per million? I'll get to the point where I probably just use one or the other, but I stress that because they are equal. What is a concentration in parts per million of a sludge that has 3% solids? So if it's 3%, if 1% is 10,000 milligrams per liter, then 3% is going to be 3 times that much, which is 30,000 milligrams per liter or parts per million. Now, if we have a sludge that has a solids concentration of 7,000 parts per million, what would that concentration be as a percent? Well, if we know that 1% is 10,000 parts per million, and we divide 7,000 by 10,000, that means we're going to get 0.7. And we have to remember that's 0.7% because the 10,000 is equal to 1%. So we're 7/10 of that when we talk about 7,000. We can express 5% concentration as both a fraction and as a decimal. And so 5% is simply 5 divided by 100. We can reduce that down to 1 divided by 20 by dividing both the top and the bottom by 5. We divide 5 by 5, we get 1. We divide 100 by 5, we get 20. So it's equal to 1/20th. And then as a decimal, 5% is basically 5 divided by 100. You put that into your calculator and you get 0.05. So that's the decimal equivalent. So we are already up for our first poll. The first poll is a return sludge has a concentration of 6,200 parts per million. What is the percent concentration of this sludge? All right. So we've had 82% of the people have responded. So we're going to share the results and go through the problem. So we have 77% of the people said 0.62%. We've got 15% at 15% at 6.2%, 7% at 0.062%. You can all see that. I will just go on to working the problem. All right. So the solution is simply if we take our 6,200 milligrams per liter and we divide that by 10,000 milligrams per liter, that's going to give us 0.62%. So that is what the vast majority of people had for the answer. All right. So we'll move back to the slides. I will stop sharing the results. And as you can see here, 6,200 milligrams per liter divided by 10,000 milligrams per liter equals 0.62%. All right. So now we're gonna look at the pounds formula, and this is something that is used quite a bit. It can be kind of lengthy. So as you see this formula come up, I encourage you to take note of it, write it down. It'll be used quite a bit throughout this. So the pounds formula is used to calculate amounts of solids in wastewater and chemical dosages. It's used in water, drinking water as well. But for wastewater, we can look at things like influent and effluent concentrations of ammonia, BOD, total suspended solids. We'll talk more about mixed liquor solids concentrations and activated sludge. It's good for chemical feed and dosage. And the formula is the flow in million gallons a day multiplied by the concentration in parts per million or milligrams per liter multiplied by the weight of water of a gallon of water. So 8.34 pounds per gallon. And that's going to give you an answer that's in pounds per day. So this is an important formula. We'll use it quite a bit. And as far as our units go, the units of flow are going to be, remember, they're going to be in million gallons per day. So if they give them to you something else, you need to convert 2 million gallons a day. And our concentration is parts per million or milligrams per liter. And for the most part, we're going to assume that everything that we're working with is 8.34 pounds per gallon, the same as it is for clean water. It would vary slightly, but not worth really us being too concerned about based off what we're doing. So these are some of the things that we have to make sure we're in these units and that these are the numbers that we're using. So we'll look at a calculation using the pounds formula. We have a wastewater treatment plant. It discharges a treated effluent into a nearby river. The discharge has an average flow of 0.4 million gallons a day and a BOD concentration of 15 parts per million. Approximately how many pounds of BOD are discharged into the river over an entire year? So let's look at this solution to this problem. What we're going to do, our pounds formula is going to be 0.4 million gallons a day multiplied by the concentration of the BOD, which is 15 parts per million, and then multiplied by the weight of a gallon of water at 8.34 pounds per gallon. We multiply that out. What happens is our million from the million gallons cancels out with the parts per million. The days are carry through, even though it doesn't appear as they should. And we end up with 50.04 pounds per day. Now, if we want to know how many pounds there are in a year, we're going to have to convert from days to years. So in order to do that, we're going to take and multiply by 365 days per year. So we do that, we're cancel out our days. and we're going to get an answer that's in pounds per year. We do that calculation, it's 18,264.6 pounds per year. So that's how many pounds of BOD are discharged into the river in an entire year. So the pounds formula is great, and it's if we have some different things, we can figure out some. If we have certain things, we can figure out other things. We can manipulate our equations so that in this case, we're not solving for pounds per day, we're solving for the concentration. And in order to do that, we're going to divide each side. We would have divided each side of this equation by concentration to get to manipulate them around. And so our concentration in this case is equal to the pounds per day of solids divided by the flow times 8.34 pounds per gallon. And actually, it's not as simple as that, but this would be another, as far as how we get from pounds per day to concentration, it's not quite that simple, but it's another formula that I would recommend you write down, and because we'll be using this one as well. But it allows us to, if we know our pounds per day of solid and we know our flow, then we can get our concentration. So in this case, we've got an example of a gas chlorination system. It delivers a feed rate of 10 pounds per day gas chlorine to a wastewater effluent flow of 0.9 mgd. What is the dose concentration of chlorine in parts per million? So we, in this case, we know the pounds per day. We've got 10 pounds per day, and we know that our flow is 0.9 mgd. So we can plug those in, and it will give us our concentration. So if we do that, we put the 10 pounds per day chlorine, we divide that by 0.9 mgd per and 8.34 pounds per gallon, and it gives us 1.33 parts per million. So we'll look into the pounds formula a little bit more. We want to consider 1 million gallons of wastewater with a concentration of 300 parts per million of total suspended solids in this case. The total suspended solids is 300 millionths of the weight of each million gallon of water. So what is the weight of a million gallons of water? We can find that by multiplying a million gallons by 8.34 pounds per gallon, and we'll end up with a number of pounds. We do that, and we get 8,340,000 pounds, and that's how much a million gallons of water weighs. Now we want to know what is the weight of the TSS, the total suspended solids, in each million gallons of the water. So we know that we've got 300 parts. So if we take those 300 parts, we multiply that by the 8,340,000 pounds, and then we divide it by a million parts of water. So that's our 300 parts of TSS per a million parts of water. We multiply that out, and we get 2,502 pounds of total suspended solid. To write this using the pounds formula, it would look like 1 million gallons a day times 300 parts per million times 8.34 is equal to 2,502 pounds. And the formula works in this case because the million and millionths cancel and the solids concentrations are small. They don't really change the density of water. If they were significant, then we would probably need to change the density. We would use a number, potentially greater than 8.34. But for most cases, how much more dense that is not significant, and it's easy to use this 8.34. So now we're on to our second poll. It's a pounds formula poll. So I'd recommend that you have that pounds formula handy. And the poll says a raw wastewater influent to a treatment facility has a flow of 1.2 million gallons a day and contains an ammonia concentration of 15 parts per million. How many pounds per day of ammonia is entering the treatment facility? And a spoiler, I would recommend you look at you have that pounds formula, the original one that we mentioned, and that should help you get this. All right, so we're going to look to solve this problem, and I'll solve it, and then I'll share the results after that. So as you can see here, we're going to use the pounds formula. So the pounds is going to be equal to the flow in million gallons a day times the concentration in parts per million times 8.34 pounds per gallon. So we simply put in our numbers. We've got 1.2 mgd. We're going to multiply that by the concentration of 15 milligrams per liter or parts per million times 8.34 pounds per gallon. We do that, and I get 150.1 pounds per day. So this was based on a full day of ammonia. So let's see what we have from the poll. I will share the results. So we have 83% of people said 150.1 pounds per day. We had the next most popular answer was 134.6, I believe, and that was 12%. Okay, well, thank you. We're gonna, as I said, we're gonna keep going with the pounds formula. We'll use this quite a bit today in various shapes and forms, and this is what you would see on your on the version of the slides that will be shared. So the next thing we're gonna talk about is secondary wastewater processes. In secondary treatment, the organisms that are in the water, mainly bacteria, consume organic matter in the wastewater. What this does is it prevents the depletion of oxygen when we discharge those waters that the water goes into, the receiving waters. We don't want to take and deplete that oxygen, which is what happens in the treatment. We don't want that happening out into a river, lake, stream, that type of thing. And we're also getting rid of any potential pathogens. In secondary wastewater processes, the BOD is consumed and it creates a cellular biomass. In this case, the microorganisms also help with flocculation and settling. They help that all settle out, and certain types of bacteria can nitrify ammonia, which is also it would take the ammonia out of the water that's getting discharged to a river, lake, or stream. So let's talk about biochemical oxygen demand, BOD. So BOD indicates the strength of a waste stream in parts per million. So BOD is the food that microorganisms consume during the wastewater treatment process. So these bugs need food to eat, and BOD is how we look at that food. We've got this little bug here. It takes in oxygen, it takes in BOD, and that's how the food is broken down. I still find it funny that we talk about food when we're talking about wastewater, but that's what we call it. So BOD is determined in a 5-day test that measures how much oxygen is required by bacteria in order to break down those wastes. There's just some examples of some test procedures and what things might look like in a laboratory. So BOD test, we take a sample of wastewater, we add it to a test bottle. For example, 10 milliliters of sample that's added to a 300 milliliter test bottle, and that I'll slide over your side there. That decimal volumetric fraction, the P in that case would be equal to 10, the sample size divided by the amount of the test bottle. So 10 divided by 300, or 0.033. So the dissolved oxygen concentration is measured at the start of the test and at the end of the test when we complete it. So in this example, we tested it at the start, and we had a DO concentration of 9.85 parts per million, and at the end we had one of 3.42. So that obviously dropped by 6.43 parts per million. And we need to adjust that because our numbers are based off of our sample size, but we want to know what it's like in actual parts per million. So we take the BOD is the difference, the 9.85 minus 3.42 divided by our 0.033. And that tells us that we've got a concentration of 194.8 parts per million. So now we're going to bring the pounds formula into our example. We've got a wastewater treatment plant that has an inflow of 600 gallons per minute, and it's got a BOD concentration of 194.8 parts per million. How many pounds per day of BOD are entering the treatment system? So the first thing we need to make sure our units are correct and consistent. So what we're going to do is we're going to convert the flow. If you remember, the pounds formula requires it to be in million gallons a day. So the first thing we're going to do is convert our flow. So if we've got 600 gallons per minute, and we know we calculated yesterday, there's 1,440 minutes in a day, that will take and convert our formula to gallons per day. So it goes from gallons per minute to gallons per day. And then we divide by the million gallons per mg is going to get it into our big mg. So we do that calculation and we get 0.864 mgd. So that allows us to then use the pounds formula because we have that now in million gallons per day. So if remember, a pounds formula is going to equal the flow in million gallons per day times the concentration in parts per million times 8.34 pounds per gallon. So we throw those numbers in, and we've got 0.864 times 194.8 times 8.34. And that tells us that we have 1,403.7 pounds per day of BOD entering the treatment system. So now I think we talked a little bit about this, but organic loading is going to be, we're going to take and look at organic loading. And what organic loading is that's the pounds per day of BOD over either the surface area or volume, depending on what we need. The different situations we'll look at it at surface area, and others we'll look at volume. The amount of BOD applied to the area or volume of a basin and a treatment process. So it's used to design the treatment system, and it's also used to optimize the processes that we have. So we want to make sure that it's designed properly, and we also want to make sure that it's working right. Yesterday, I told you we had this. We were talking briefly about trickling filters, and we have this neat photo. So trickling filter is kind of what it says it is, and the idea is that the water comes in, the effluent comes in, and it sprays over this media. It could be some sort of a stone. It could be a pellet, a plastic pellet. It could be different things, but the media has a biofilm that's growing on it, and the water obviously has nutrition for the bugs and things that grow on the media, and so the water goes down across the media, and they take up that the nutrients from that and process that. And so that's how a trickling filter in general works. I mean, it's important. It needs to have airflow. The whole thing needs to be wet. We don't want dry spots. So wastewater sprayed over the media, and the attached biofilm consume the BOD. Now, in trickling filters, you can't have too much BOD, and you have to have enough water. If the flows are too high, you have the chance that you'll scour this biofilm off of the media. So it's important that for BOD, the loading range is 5 to 25 pounds per day of BOD per 1,000 cubic feet of water. So here's our organic loading is equal pounds of BOD per day divided by 1,000 cubic feet. All right, so we can look at organic loading on a trickling filter. As we said, it's pounds of BOD per day divided by 1,000 cubic feet. When we divide the pounds per day of the BOD in the filter volume in cubic feet, we get the loading per cubic foot. And so we want to know what that is per 1,000 cubic feet. So we have to multiply by 1,000 to convert that and get the correct units. So next we'll look at an example of that. Organic loading calculation. A trickling filter receives a total flow of 0.85 mgd with a BOD concentration of 95 parts per million. Calculate the organic loading to this plant in pounds per day per 1,000 cubic feet if the trickling filter has a diameter of 100 feet and a media depth of 6 feet. So we can do our pounds per day of BOD calculation first. So that's taking the 0.85 mgd, our flow. We know that we have 95 parts per million concentration of BOD, so we multiply that and then multiply by 8.34, and that'll give us the pounds per day of BOD. It's 673.5 pounds. Now we also have to take in consideration what's the volume of our filter. So the filter is it's got a diameter, so therefore it's a cylindrical filter, and it's got a depth. So we're going to look at we need to determine the volume of that filter. So if you remember back to the cylinder, or the formula for the volume of a cylinder, it's that 0.785 times the diameter squared times the height or the depth of this. So that's going to be 6 feet. So we do that calculation, and we'll find that we have 47,100 cubic feet of filter for this BOD to go through. Now, if we're going to look at organic loading, we need to take the pounds per day of BOD and then divide that by the volume of the filter and make sure that we multiply it by that 1,000 so we get it in per thousand rather than what it comes in. And so if we do that, we get 14.3 pounds per day per 1,000 cubic foot of filter. So the things to note, we have a recommended range for that of 5 to 25. So that's well within our range. And I noticed that I had mentioned that we can dilute our recirculate with recirculation water because we don't want to have those BOD concentrations to be too high. So, and the other thing that's important for recirc water is to make sure that the whole filter is wetted, so none of the filter dries. So, once again, we had talked yesterday about recirc, and here we are again. We're using recirc water to make sure that we have the volume of water, the flow that we need. So now we'll be on to our next slide is going to be another poll, and it's on organic loading. So make note. Hopefully you jotted down the formulas and how we do this because it'll be very similar. So on to the next poll. So here we have a trickling filter with a diameter of 75 feet and a media depth of 8 feet. It receives a total flow of 0.35 mgd with a BOD concentration of 115 parts per million. We want to know what the organic loading is in pounds per day per 1,000 cubic feet. Okay, so we will look to work the problem here, and then we'll cover the results, what you guys came up with. So the first thing that I would want to do here is I want to figure out the pounds per day of BOD. So pounds per day is going to be our million gallons a day. So 0.35 mgd multiplied by our concentration, which is 115 parts per million, multiplied by 8.34 pounds per gallon. All right, so we do that, and I come up with 335.7. And that pounds of BOD per day. So the next thing we want to do is figure out what's the volume of our filter. So we've got it's got a 75-foot diameter, and it's got a media depth of 8 feet. So our volume is going to be equal to our 0.785 multiplied by the diameter times the diameter times the depth of 8 feet. And that gives us 35,325 cubic feet. All right. So organic loading, if we remember that, that's going to be the pounds per day, which in this case we've said is 335.7 pounds per day, divided times 1,000, because we want to make sure we get it in the right units, divided by our volume, which is 35,325 cubic feet. So we do that calculation, we'll drop it down here. Hopefully everybody can see that. And I come up with 9.5 pounds per day per 1,000 cubic feet. Okay, let's go to the poll, and I'll share the results of the poll. It looks like we have 71% of respondents said 9.5 pounds per day per 1,000 cubic feet. All right. And if we move on, this is the solution that will be in your in the PDF of the PowerPoint. And note that the organic loading is within the 5 to 25 range. That's what our goal is, to be in that range, and we are within that range. So as there were things that we talked about in evaluating primary clarifiers, there's also some things that we want to look at when it comes to secondary clarifiers. They're similar, but there's a couple of different things that are different. The weir overflow rate parameter is lower in the case of secondary clarifiers, and we also have a solids loading parameter. So there's the weir overflow rate, and it helps to ensure that solids will not be carried over into the final effluent. So it's a big deal to make sure that we're not having these solids end up going into our final effluent, which would, is potentially discharged directly to a river, lake, or stream. Now, the solids loading rate, that's in pounds per day of solids, and enter the clarifier, and we're dividing that by the clarifier area. So here we've got a diagram that shows an aeration and secondary clarifier. You can see you've got the influent coming in. We've got this MLSS. That's the mixed liquor suspended solids. Those are the solids that enter the secondary clarifier. Wastewater flows. The influent flows into the aeration tank. There's air added in the aeration tank. And then it goes from there to the secondary clarifier, where the mixed liquor suspended solids settle out. But in We consider that there are mixed liquors, suspended solids in both the aeration basin or tank and the secondary clarifier. The solids loading formula measures whether the solids applied to the clarifier is within the correct range. So it's another test that we can do, a check against our process. So we're going to look more into solids loading rate in a secondary clarifier. So we've got an example, and we're going to work through a problem here. We've got a secondary clarifier with a diameter of 72 feet. It receives a flow of 2.9 million gallons a day with a mixed liquor suspended solids concentration of 2,800 parts per million. What is the solids loading rate in pounds per day per square foot? So obviously we look at this, they've given us a base. We know we can calculate the area of our clarifier because they've given us the diameter. Solids loading rate is in pounds per day of mixed liquor suspended solids divided by that area, the surface area. So first we'll look at determine the pounds per day of solids that are entering. We do that through our pounds formula. We take the 2.9 million gallons a day, multiply by the concentration of 2,800 and multiply that by 8.34 pounds per day. And we get 67,721 pounds per day. Now we need to know what the area is. So we can divide the pounds per day by the area. To determine the area, we simply take our 0.785, we multiply it by the diameter twice, or diameter squared, however you want to look at it. And that'll give us an area of 4,069 square feet. So our solids loading is going to be taking and dividing the 67,000 by the 4,000. And that gives us 16.6 pounds per day per square feet. So we're going to do several different types of, we've got two other types of problems that we're going to do like this, and they're all very similar. So as we go through this, I'd make sure to make a note of how we work this problem, determining the pounds per day, the area, and then in this case, solids loading, but that will change as we go through some of the other problems. So we've got another example. We've got a secondary clarifier. It's got a diameter of 60 feet in this case. It's got a depth of 10 feet. So that tells me we're probably looking at volume here because we have both the diameter and the depth. And we've got a flow of 3,256 gallons per day. The mixed liquor suspended solid concentration is 3,226 parts per million. This clarifier is not performing optimally. Determine the following. So the first thing we're going to have to determine is the detention time in hours. Remember, we're looking at 2 to 3 hours. We're going to have to determine the surface loading rate in gallons per day per square feet. And we have our recommended for that is 300 to 1,200 gallons per day per square feet. We're going to have to determine our weir overflow rate in gallons per day per foot, and that's recommended between 5 and 15,000. And then we have to do our solids loading rate in pounds per day per square foot, and that's recommended at 12 to 30 pounds per day. So I may have jumped the gun in the next few, we're going to cover these type of formulas in evaluating a secondary clarifier like this. So be on the lookout. In this case, our flows, we've got our flow down here. We got our concentration. We've got our depth. We've got our the diameter of our clarifier. So using that information, the first thing we're going to do is we want to determine what the detention time is based off the information that we were given. So from yesterday, we said that detention time is equal to the volume in gallons divided by the flow in gallons per hour. So our volume is 0.785 times 60, which is the diameter, times 60, times 10, which is the depth, times 7.48 gallons per cubic feet. So that's going to, our feet are going to cancel out, and we're going to be left with a number that's in gallons. So we do that calculation, we get 211,384.8 gallons. The next step is we need to know what our flow is. And we're given our flow in gallons per day, and we want to know our detention time in hours. So we're going to need to convert that to hours. And we do that by multiplying by 1 day for 24 hours. So that'll remove our day, and it'll give us a number in gallons per hour. It's 135,667 gallons per hour. And our detention time is going to be taking the number of gallons that we had, and we divide that by the number of gallons per hour. So the total number of gallons by number of gallons per hour that we have. And so that gives us an answer, a detention time of 1.56 hours. So what would be your conclusion on that? Well, our detention time is slightly lower than what our minimum was. Remember, we want it to be a detention time of between 2 and 3 hours. And so what happens if we don't have enough detention time? It's likely that we're not going to get the proper settling, and things will carry out through our secondary clarifier and potentially get discharged. So that's not good. Now we're going to look at that same secondary clarifier, but at this time we're going to look at overflow rates. All right. So our surface overflow rate is equal to the flow in gallons per day divided by the area in square feet. So we take our same basin or our same clarifier, and we're going to determine first the area. We determine the area by multiplying 0.785 times the diameter squared, and that gives us an area of 2,826 square feet. From that, we're going to divide our flow in gallons per day by the area that we were given. Or that we calculated rather. So our flow is in gallons per day is 3,256,000. Our area of our clarifier is 2,826 square feet. So it gives us an answer of 1,152 gallons per day per square feet. So how does that compare to what is recommended? Now, our recommendation, we were recommended that it's between 300 and 1,200 gallons per day per square feet. So we're within the range, but we're kind of on the high side. So it's probably not a real comfortable place for us to be. We have the potential that we are going to overflow solids and that's not where we want to be. So we may want to make a process change so that we can reduce that down. And so we've got our overflow rate is not as high. Now that could be, we could potentially reduce our recirculation rate. Maybe that's an answer to how to fix that. And then the third of these is we're going to look at the weir overflow. So we have the same set of conditions, the same clarifier. So the weir overflow rate is the flow divided by the length of the weir, or that's the circumference in this case. So now we're going to have to determine what the circumference is. So we've done the volume, we've done the area, and now we're going to look at the circumference. So circumference or weir length is equal to pi times the diameter. So 3.14 times 60. So there's circumference, or the length of our weir for our clarifier is 188.4 feet. Now we divide that flow by the flow that we had, same flow that we used on the other two examples. That's 3.256 million gallons a day. and we divide that in gallons per day by 188.4 feet. So that gives us 17,282 gallons per day per foot. So what do when we look at that, the rear overflow rate, the top of our recommendation is 15,000 gallons per day per foot. So that tells us that our water is probably flowing at too high velocities, and those solids are probably going to be exiting our secondary clarifier and going into our effluent. So we would need to make some process changes. So the next poll that's coming up involves a secondary clarifier evaluation, and we're going to be looking at solids loading. So let me just go back here before it's probably not the most efficient way to do this. So I want to look at the solids loading. So everybody, this is what we were looking at. That's when we went through this. So when we do the problem, you're going to want to work something similar to that. So in our example, we have a secondary clarifier with a diameter of 60 feet, a depth of 10 feet, and a flow of 3,256,000 gallons a day. Our mixed liquor suspended solids concentration is 3,226 parts per million. The clarifier is not performing optimally. Determine the solids loading rate in pounds per day per square feet. Okay. Looks like we've got a good number of our participants have responded with the poll, so we will move on and look at the solution to this. So if we're going to look at it, one of the things that we have to take in mind is that solids loading rate recommended is between 12 and 30 pounds per day per square foot. So that's what our goal is. Let's see what we have for our answer. So solids loading is equal to our pounds per day of our MLSS divided by the area of our clarifier. So in that case, we've got our first step is determine the pounds per day entering the basin, and we need to use our flow in million gallons per day. So if we take our flow of 3.256 MGD, because it has to be, for the pounds formula, it has to be in million gallons a day. We multiply that by our concentration of 3,226 parts per million. And we multiply that by our 8.34 pounds per gallon. We get 87,602 pounds per day. All right. So we also need, in this case, to know the area of the basin. So our area of a cylinder is equal to 0.785 times our diameter, in this case 60 feet times 60 feet. And we get from that 2,826 square feet. So solids loading, if we go back to here, pounds per day, which is right here, 87,602 pounds per day. And then we need to divide that by our 2,826 square feet. And that gives us an answer of 31 pounds per day per square feet. So as we said, our goal, our ideal is between 12 and 30. So obviously this is, we thought there was a problem. There is a problem. We've got where our loading is too high. So we would have to go about figuring out a way to fix that. And that could be lowering the rate of that we're bringing in of our mixed liquor suspended solids, reducing that, increase the any recirc water, that type of thing. So that being all said, let's look at our polls. We're going to share the results. So 31 pounds per day is we have 77% say that. We've got a mixed bag. We've got 8, and 7% for the other answers. So at this time, I think we're about in a position to take a 10-minute break. And the range is between 12 and 30. So we'll take a break here for 10 minutes. And we will come back at or around 2:21 Eastern time. Hello. All right, we're back. So now we're going to move on to our next set of topics. We're going to look at some other process control calculations. We'll look at mean cell residence time, abbreviated to MCRT. We'll look at the FM, or the food to microorganism ratio, and we'll look at the SVI, or the sludge volume index. So inactivated sludge processes where our controls, we're going to look into what different things we can do to help understand the treatment process, and the math that's involved will help with that. So here's basically the activated sludge process. We take the water comes in, the wastewater comes in into the preliminary treatment. And here we experience some screening, some grit removal, taking out the large things. The next thing we do is we go into the primary clarifier, and that's where the settleable solids are removed. And we send those off. We take those off, and we handle those separately. The water that goes on is considered the primary effluent. And as we said, the settling time for a primary clarifier is usually between 1.5 hours and 3 hours. The primary effluent goes on. And so we've got this area here, and that's where we handle the non-settleable solids, the suspended solids. That's the total suspended solids, the BOD. We convert our waste to cellular biomass, and the time that it takes in there, the settling time, is typically between 2 and 4.5 hours. From there, we go on to secondary effluent leaves, and we can do disinfection and discharge. We can do a tertiary treatment, coagulation, filtration. We can look into recycle and reuse. So that's in general the process that's involved with activated sludge. So we'll look at it a little more detail. So we've got the aeration tank, and the aeration tank includes that mixed liquor suspended solids. The waste activated sludge is mixed liquor suspended solids. Primary effluent comes in, goes to the aeration tank, into the secondary clarifier. And then we have return activated sludge. So we're gonna either waste the sludge, or we're going to return it back into the primary effluent, and it'll go through the process again. That returned activated sludge is added to the aeration tank to maintain a high stable concentration of biomass that'll consume the organics that are in the water. As I said, we're going to combine that return activated sludge with the mixed liquor suspended solids and they go into the aeration tank and onto the secondary clarifier. What are the main components of activated sludge? We've got that aeration tank where we combine MLS with a return activated sludge. We add air, and that creates the biomass for the organisms. We've got a secondary clarifier, and that's where that biomass it settles out as sludge. We can either return or waste that activated sludge. So some goes back as return activated sludge back through the process, and others goes out and gets dealt with as sludge. So in the aeration tank, we've got food in the incoming wastewater, and we've got these hungry bugs, which are found in that return activated sludge. So we bring them back to make sure that we've got the proper concentration of bugs to food by returning that waste back through the aeration. Incoming raw wastewater is mixed with return activated sludge to create a mixed liquor. Then we apply the aeration to promote that metabolism of the waste by the bugs that are in the aeration tank. The BOD is consumed by the microorganisms and converted into biomass. That's what happens in the aeration tank for activated sludge. Here's a photo that kind of shows what a aeration tank might look like. And as you can see, we've got the primary effluent that comes in, and we've got the return sludge that's added there too. So the return sludge is much darker. By comparison, the primary effluent actually looks clean by comparison to the return sludge. So in the secondary clarifier, we've got the mixed liquor that's discharged from the aeration tank, goes into the secondary clarifier. After the aeration, we've removed BOD, converted into this cellular biomass, and the biomass is sent to the clarifier so that it can settle out. The final effluent in this case from the secondary clarifier is in essence the clean water that can hopefully be discharged. It's possible there will be some additional treatment, as we mentioned, tertiary treatment that has to be done. But we end up settling out the solids. These are all hungry microorganisms they're hungry, and depending on how much, whether we need it for return activated sludge, we'll bring it back to before aeration. And if not, it'll go to waste. That's the part that we don't need. And so it's all important. It's a balancing act to figure out which, do we need to return it? Do we need to waste it? And as we go through that, it'll hopefully make a little bit more sense. So there's a couple of things that we look at. We look at the food to microorganism ratio, and we look at the mean cell residence time. So the food to microorganism, the mean cell residence time is, it's kind of one we talked about detention time before. It's similar to that. It's the idea, but it's with solids. So we're looking at how long these solids stay in the process. Now, the food to microorganism ratio is the pounds of BOD that are entering that we have in treatment divided by the pounds of that mixed liquor volatile suspended solids that are in the aeration tank. So that's the food is the BOD, and the organisms are in the MLVSS. That ratio is important to how we process. So we'll first delve a little deeper into the mean cell residence time. That's the pounds of MLS in the system divided by the pounds per day of solids that leave the system. And those solids leave through through wasting, waste activated sludge, and there's also some solids, unfortunately, that are gonna leave in the effluent. It's pretty difficult to avoid. It's difficult to avoid not having that happen. So if we want to increase the mean cell residence time, we decrease how much we're wasting, and so that means that our solids are going to be held longer. Fewer of them are leaving, more of them get returned. If we want to decrease, we're going to increase how much we waste, and that means that our solids are going to stay in the system for a shorter amount of time. So increasing the MCRT promotes slow-growing microbes, enables better nitrification, or ammonia removal, and reduces the sludge production. And reducing the MCRT, we use that to prevent excessive sludge age. We don't want these things to get too old, and it can help reduce operational costs and control some of the operational problems that can come along. All right, so we're back on looking at the activated sludge process. Solids remain in the systems longer than in the liquids because a portion is returned. As we've said, some of the solids come back in that return activated sludge. Some are wasted, but the liquids all pretty much head through the system. So we have an example. Suppose that we had 20,000 pounds of solids continuously maintained in the activated sludge system. That's combined the aeration tank and the secondary clarifier. And we had 4,000 pounds a day of solids that leave the system as waste activated sludge. So what we're going to have is the average time that the solids remain in the system, or the mean cell residence time, is the weight of the solids in the divided by the solids that we're taking out, or the waste activated sludge. So that's the 20,000 pounds up here divided by these 4,000 pounds, and that gives us 5 days. So that means that that those are sticking around for 5 days under that in that scenario. MCRT is the pounds of solids under aeration divided by the pounds per day of solids that leave the system. The solids under aeration are both the aeration tank and the secondary clarifier, because they both have the same mixed liquor suspended solid. Solids leaving the system include waste sludge flows and solids in the effluent. We hope that there aren't many solids in the effluent, but they're unavoidable. So if we want to look at the full formula, and this is another one that I would suggest writing down. It's a long formula, but the MCRT is equal to the million gallons in the aeration, the million gallons in the clarifier, multiplied by the MLSS concentration times 8.34 pounds per gallon. Pretty much sounds like the pounds formula, except for we're adding the two together. And then we're going to divide that by the pounds per day of suspended solids in the waste activated sludge. And we're going to add the pounds per day of suspended solids in the effluent. The top of the formula, we can add the aeration and clarifier volume, because that MLS concentration is the same in both of those. And we have two, on the bottom, we have two pounds formulas, one for the waste activated sludge and the other for the solids that are exiting with the effluent. So hopefully you've had a chance to take note of that. We're going to work on an example problem of this. So we've got a lot of information. We're going to determine the mixed cell residence time of an activated sludge treatment plant that has the following information. So we've got a flow of 3.25 million gallons a day. We've got an effluent suspended solids concentration of 21.2 parts per million. We've got an aeration tank volume of 1 million gallons. We've got an MLSS concentration of 2,050 milligrams per liter, or parts per million. We've got a secondary clarifier operational volume of 0.25 million gallons. We've got a waste activated sludge flow of 0.055 million gallons a day. And we've got a waste activated sludge concentration of 7,980 parts per million. A lot of information. So our formula, again, aeration tank, a million gallons of that, plus the clarifier, times the MLS concentration, 8 times 8.34, the WAS, million gallons a day times its concentration times 8.34. And then we add that to the effluent MGD times the concentration times 8.34 pounds per gallon. So we plug those in, and this is what we get. Now, one of the things that we can do to kind of simplify this, if you wanted to, the math works out so that we can actually take the 8.34 pounds per gallon out of this, because the way the math works out, when we multiply these together and then we add them to, and we're multiplying here and we've got them on top, they all cancel out. So if you want to simplify this, you could. The important thing, though, is that it only works if that 8.34 pounds per gallon doesn't change. If for some reason we said that it works in general, I mean, this isn't the same as pure water, but it's pretty close. If for some reason those changed, you would have to keep them in. But this could be a little simplified if we did that. So so we want to solve the formula. We end up with 21,371.25 pounds MLSS in the system. And we've got 3,660.4 pounds of the waste activated sludge. And we've got 574.6 pounds in the effluent. That gives us, when we add these together, we get 4,235 pounds per day total between both of those. We divide that into the number of pounds in the MLSS of 21,371, and we get just over 5 days. And the pounds cancel, which leaves just the days in this case. All right, so now we're going to look at the mean cell residence time in conventional activated sludge. Now, in that case, our goal for that is it's going to be between 5 and 10 days. The solids are held for a shorter amount of time. So we're for conventional activated sludge, it's a shorter time for that residence time. We've got higher aeration rates typically associated with those. With that treatment, we've got a higher FM ratio, the food to microorganism ratio. And we're treating some of the simpler types of organisms, the bacteria and ciliates. These types of treatments require a much smaller area, a smaller footprint, and a higher rate of treatment. So they're helpful in areas where you don't have a lot of space. Now that is in comparison to mean cell residence time in extended air activated sludge. So in extended activated sludge, those residence times are closer to 15 to 25 days. So that means everything stays in our system longer in our process, our treatment. The aeration rates are lower, the FM ratio is lower. And we deal with, because of those extended times, we find more complex organisms, the protozoa and rotifers. And this type of treatment takes a much larger area, a larger footprint. This is most likely an oxidation ditch. These things can be, the size of a football field, for instance. And so they can be quite large. But it goes through this instead of we look back the treatment, we had aeration before, just a smaller tank. Now we've got a large area where it just slowly flows around. But we still end up with the clarifier. We still have return activated sludge. We have waste activated sludge. So our next poll. Determine the mean cell residence time of an extended air activated sludge treatment plant given the following. We've got a plant flow of 0.9 million gallons per day. We've got an effluent suspended solids of 17.5 milligrams per liter parts per million. Aeration tank volume of 1.2 mg. Mixed liquor suspended solid concentration of 3,760 parts per million. Secondary clarifier operational volume of 0.24 mg, waste activated sludge flow 0.037 million gallons a day, and the waste activated sludge concentration of 7,980 parts per million. And I'm not sure if you'll be able to see this with the poll, but we will. Whoops. I don't know. Would like to. Maybe we'll go back and show you, if I can, the formulas that you'll need to use. Okay, so we're gonna work through the problem. I'm taking note of the idea to have that formula because it is so involved and it's so long. To have that included with the poll. Um, because really it's not so much memorizing the formula as it is understanding where the parts and pieces go. So that's a definitely something we're always trying to make these trainings better for you. One of the parts was the idea that maybe we would show, like as I'm doing to work the problems, maybe that helps slow process down and helps people understand how things are done. So as far as solving this problem, we're gonna take we need to have the number of million gallons from the aeration tank. So that's 1.2 million gallons. We need to have our 0.24 million gallons that comes from the secondary clarifier. And then we're going to multiply that by the concentration of the mixed liquor suspended solids. That's 3,760 parts per million. Then we're going to multiply by 8.34 pounds per gallon. On the bottom of the equation, we needed to have the waste activated sludge flow. That's 0.037 million gallons a day. We're going to multiply that by the concentration of the waste activated sludge, 7980. Multiply that by 8.34. And then we are going to, we need to take the total plant flow of 0.9 mgd, multiply it by the effluent concentration, which is 17.5 parts per million, and multiply that by 8.34. So as I had said, from a math standpoint, we can actually we can cancel those out if we wanted to. You could, if you do want to do the math, you can do them without those, with and without that in there, and you should end up with the same result. So if we go through this, on the top, we're going to get 45,156.1 pounds MLSS. As far as the top goes, on the bottom, the two numbers we're going to be adding 2,462.5 to 131.4. Those are the pounds of the waste activated sludge and the effluent. So if we divide those out, we get 17.4 days. So let's see how that compares to our poll. So 71% of the people said 17.4 days. And share those results. Okay. Well, as I said, I apologize that the intent was not for you to memorize the formula. Hopefully you wrote it down, but it's to know where to plug everything in. So if we advance through the solution that was done on the slides, we've got that. And the information that we get from that, it can help us to operate the plant at its best capacity. We can increase or reduce the waste activated sludge, as we've said, those concentrations or flows, so that that'll change that mean cell residence time. So we've talked about mixed liquor suspended solids. Well, we also have what's considered mixed liquor volatile suspended solids. And so the mixed liquor suspended solids is a concentration of solids in the activated sludge system. We use that in calculating that mean cell residence time, and it's determined by filtering solids from a mixed liquor sample, drying and weighing the solids. So in that case, we've got the weight of the mixed liquor suspended solids in milligrams divided by our liquid sample, the volume in liters, and that gives us the MLSS in parts per million. So as you can see from this diagram, we've got our total suspended solids. We've got a filter. There's a vacuum placed on this, and it pulls this down. Dissolved solid, total dissolved solids end up on the bottom. Total suspended solids end up on top on this filter, and that's how we separate those out. So we've got an example. We collect a 25 mil MLSS sample from an aeration tank. After the solids are filtered and dried out, they are found to weigh 67.5 milligrams. Dividing the weight by the sample volume will give us milligrams per milliliter, and we want those in milligrams per liter. So we're going to have to multiply that, the answer that we get, by 1,000 milliliters per liter. So if we take our 67.5 milligrams, we divide that by our sample size of 25 milliliters, that gives us 2.7 milligrams per milliliter. And then we multiply that by 1,000 milliliters per liter, and gives us 2,700 parts per million mixed liquor suspended solids. Now, our mixed liquor volatile suspended solids is it's the organic portion. So that's the part of it that's that it's organic, that's biological, and that represents the microorganisms that are in it. We need that in calculating this FN ratio, the food to microorganism ratio. And we determine that by placing the dried MLS solids in an oven, which volatilizes and burns off that volatile portion. So we look here, we've got a portion of it's going to be it's going to volatilize off. We're going to have the non-volatile solids. We're going to have the volatile solids that come off. It's usually around 70% of the concentration is the volatiles. Let's get this to advance. Our PowerPoint is operating slowly. With the other 30% being ash. So it's going to remain once we go through this process. The ash stays behind. So if we look at our previous example, and we had a 67.5 MLSS solids, we placed that in our oven. We heated up to 550 degrees Celsius, and those volatile solids vaporized. They went away. The remaining ash, if we weighed that, let's say we had 22.5 milligrams. So in order to do this, we're going to take the and subtract the weight of the ash. Subtract the weight of the ash to determine the weight of the mixed liquor volatile suspended solids, and calculate the concentration of parts per million. We take our 67.5 milligrams of MLSS, subtract out the 22.5 milligrams of ash, and that gives us 45 milligrams of mixed liquor volatile suspended solids. We divide that by our original sample, multiply by 1,000 milligrams per liter, and that tells us that we have 1,800 milligrams per liter of mixed liquor volatile suspended solids. Wow, it's a mouthful. All right, so from that, we said we needed that information in order to calculate our food to microorganism ratio. And that food to microorganism ratio is the pounds per day of BOD that's entering the treatment. So that's the food. And then the microorganisms is that the pounds of MLVSS that are in the aeration tank. So what things do we know in order to do that? We need to know the BOD. We need to know the MLVSS. and we have to have the pounds formula. We've done the pounds formula several times. So what do we want as far as what are our ideal food to microorganism ratios? It depends on what type of treatment that we're doing. So if we're looking at conventional activated sludge, those plants generally operate with food microorganism ratio of between 0.25 and 0.45. So if we're looking at extended aeration plants, they usually operate with a ratio of 0.05 to 0.15. So they've got less food, but they've got more microorganisms. And that's because, as you notice, the number is lower, which means that we're dividing by a higher number, or we have a smaller number on top. So if we've got, we'll work an example here. We've got an activated sludge plant that has an influent flow of 1.5 million gallons a day with a BOD concentration of 250 parts per million. The aeration tank has a volume of 500,000 gallons and an MLVSS concentration of 2,000 parts per million. Calculate the food to microorganism ratio and compare to the target FM ratio of 0.4. So our formula looks like this. The incoming BOD divided by the MLVSS in the tank is going to be equal to the flow in million gallons a day times the BOD concentration times 8.34 pounds per gallon divided by the volume in million gallons and multiplied by the MLVSS concentration in parts per million times 8.34 pounds per gallon. So with the information that you've got and this formula, we'll give you guys, give you people a couple of minutes to work this problem on your own and see, and then I'll cover how we do that. Hello. Hopefully you had an opportunity to crunch some numbers here. So our flow in million gallons a day, we said the influent flow is 1.5 million gallons a day. The concentration is 250 parts per million. We're multiplying that by 8.34. And then the bottom, we have a volume of 500,000 gallons, and we've got a concentration of 2,000 parts per million. So as I said, you could cancel these out, the 8.34 pounds per gallon. You don't even have to cancel them out. You don't have to figure them into your, you don't have to multiply them together with your problem. So we end up on the top, we get 3,127.5 pounds per day. And on the bottom, we get 8,340 pounds, which gives us a food to microorganism ratio of 0.37. So we said the target ratio was 0.4. So it's pretty close, and it's well within that. It's within that range that we had. These things can change over time, but as an operator gets used to operating a plant, they watch for trends. They make adjustments based off of past experience, and so that's important. All experience is very helpful in operating treatment plants. And the shows that the result of the food to microorganism ratio shows that 0.37 pounds per day of BOD is added for every 1 pound of MLVSS or organisms maintained in the aeration tank. All right, so we have poll question number 6. And it's the FM ratio. So we've got a conventional activated sludge plant, has an influent flow of 1.1 mgd with a BOD concentration of 220 milligrams per liter. The aeration tank has a volume of 0.4 mg and an MLVSS concentration of 2,300 parts per million. Calculate the FM ratio. I wish that we had that formula available for you. Hopefully you have the formula sheet and you can see it on there. Okay, we're back to work the problem. So so we need to take, and first we need our flow, which is the influent flow is 1.1 mgd, and we're going to multiply that by the concentration of our BOD, which is 220 milligrams per liter, parts per million. We multiply that by the 8.34 pounds per gallon, and we're going to divide that by our volume, which is 0.4 million gallons, and our MLVSS concentration, which is 2,300 milligrams per liter. Now, when that's multiplied by 8.34 pounds per gallon. So if we multiply this out, we get 2018.3 pounds per day divided by 7,672.8 pounds, which is equal to 0.26 days. All right. That's our FM ratio, food micro ratio. Okay. Here's this advances for me. There's a solution. And this ratio is it's within acceptable limits. It is at the lower end, so there might be something going on and some reason to check on the process. If we increase the waste activated sludge rate, that'll just decrease the MLVSS, which is going to lead to a higher food to micro organism ratio. So what effects do our food to microorganism ratios have? If the ratio is too high and that means we've got a lot of food for the bugs. It can result in there's too much food for the bugs to eat, so we're not getting enough of that BOD removed. We can end up with poor settling in our clarifiers. If we have too low of a food to microorganism ratio, that means there's not enough food for the bugs. They may not survive. They're not going to be enough food there for them to take out. So we can end up once again with poor settling. So the last concept that we're gonna look at is the SVI, or sludge volume index calculation. I'm sorry. Oh, yeah. All right. I didn't share the results, but the majority of people did have the same answer. So we look at the sludge volume index to evaluate how the sludge is settling. SVI is the volume occupied by 1 gram of sludge after a settling time of 30 minutes. So SVI is equal to the milliliters settled in 30 minutes divided by the concentration, the MLSS, divided by 1,000. So for our purposes, we would like to have a sludge volume index that's between 80 and 120. That's typically produces the best settling. If we've got a low SVI, so something that's less than 50, that usually indicates that our sludge is old, potentially dense, and so that's not good. And then if it's higher than 150, it can indicate that there's we don't have complete treatment. We may have some filamentatious bugs, bacteria that are in there that could cause problems. So this graph shows a relationship between SVI and FM ratio. So conventional activated sludge plants, as we said, generally operate with an FM ratio between 0.25 and 0.45. As we can see here, and an SVI of between 80 and 120 is considered to produce the best settling. So the sweet spot tends to be in this area here. So our sludge volume index is, as we said, it's the milliliters that settle in 30 minutes divided by the concentration of the mixed liquor suspended solids times 1,000. It's probably easier to relate to and write it as it is here. So if we have an example, we've got a 1,000 milliliter settleometer, and it's filled with mixed liquor that has a concentration of 2,400 parts per million. And after 30 minutes, the settled sludge volume is 260 milliliters. What is our SVI? All right. So if we were to calculate that, we started here. This is a visual to show that we started with 1,000 milliliters and we ended up with 260 at the end. So we take our 260, we divide it by the concentration of our mixed liquor suspended solids of 2,400 parts per million, and we multiply that by 1,000, and we get 108. So our last poll question is a sludge volume index calculation. So you may want to jot these down if you haven't, and then we will move on here to the poll. A 1,000 milliliter settleometer is filled with a mixed liquor that has a concentration of 2,100 milligrams per liter. After 30 minutes, the settled sludge volume is 240 milliliters. Calculate the SVI. Okay, so we will work the problem and I will give you the results this time. And then if we get an opportunity, we will go back and cover the how people did, what the answers were for the previous poll that I didn't discuss. So we know that our SVI is equal to the milliliters settled in 30 minutes divided by the MLSS in milligrams per liter. Then we're going to multiply this by 1,000. So if we look at that, we've got 240 settled in 30 minutes. And we started out with a concentration of 2,100 parts per million. And then if we take and multiply that by 1,000, we should get 114. All right, so let's go to the poll responses. I'll share these results. And it looks as if 86% of the people said 114. We had 5% at 55, 5% at 24, and 4% at 11. Okay. Ingrid, how do we go about sharing the previous one so people can see how that went? Okay. So the results of the previous poll question were we had 83% said 0.26, and we had 14% at 0.37, 3% at 0.48, and nobody said 0.15. Okay. All right, let's see what we have remaining. All right, here's the solution. Much like we said. So we're pretty much at the end of our training. What did we cover today? We covered the Pounds formula. We covered our organic loading, activated sludge process control calculations. I feel like we did a lot more than that, but those are the key highlights. And so our main takeaways from this, what's important. We can typically only remember 3 to 5 things that come away from a training such as this. And what would we like you to remember? The 3 things are organic loading, activated sludge, and settling. And so we hope that those stick with you. And then, so as part of this, the process, especially for those to get their CECs, we need you to do a self-certification and evaluation survey for us. That survey is linked in the chat, and there's also a QR code here so that you could scan that, and you can do that on your phone as well. And this is the first time that I've attempted to do problems and show myself doing them like we did with the document camera here. So I'd be happy to hear your thoughts on that. I think the hope was that people would feel better about the fact that somebody else was doing the training, or was actually doing the work that they were training on. And so please feel free to let us know what you think about it. If anybody has any questions, we've got about 5 minutes left. And I'd be happy to answer those questions you might have. Okay, we are at 3:30. And so unless you have any problems with the survey, and if you do, please let us know. We will probably be closing the Zoom session down here. So the CEUs depends on where you're how you get them, depends on where uh, you're wanting them for. Different states have different things. Um, Pretty much for Michigan and Wisconsin people, we will take care of that. Um, as far as uh, Indiana, we will end up having to send you the form that you guys submit along with your certification to the state of Indiana.